I did not want to do a third lab remotely, and I did not want to do that one remotely. Having one or two people remote is one thing. Having all of you remote, they haven't paid me enough to do that. So we'll just push that back until next week. I did send you a homework assignment. You need that in, I have to look at the schedule for the cost path lab because you're going to use your data. You're going to use what you're digitizing as the input for the cost path lab. And if you don't have it, you can't do the lab. It was not a problem last year. It was a problem the year before. And then they're just people that just sat there and couldn't do anything because they hadn't finished digitizing. Things, you can't have any gaps in it. Your polygons gotta butt up exactly. And it has to be a single shape file or a single feature class. You can't have a road shape file and then a building shape file and then all the other ones separately. They all have to be as one. That does not mean you can't digitize them individually and then do overlays, okay? But you can't have any gaps because what we're gonna do is you're gonna take that overlay and it's going to then be turned into a raster. And if you have gaps in that digitizing, they turn into cells of no data. And the cost path will not use a cell of no data, it'll go around it. There might be reasons, you can never use this area for whatever reason, maybe but we don't have any of those on campus. If you have overlaps, if your polygons are overlapping each other, the raster only has one attribute, right? So if you have like what would be a good one? Forest overlapping open, and it's only going to take one of those values for the pixels that fall in that overlap area, and I don't know which one it would take. Okay, there's some tricks. I would for the roads, I would digitize the center lines as a separate shape file, and then I would buffer them to like, I don't know, what's our buffer? Our roads are probably 26 feet across, so 13 feet. And then you have a polygon. You could do an erase with your road buffers on top of everything else or whatever, and then sort of do a merge. It would be a reason to do a merge because we don't have any attributes really in this. Laura, have you contacted, did I give you the contact information for the zoo?
You forwarded my information to them. It's what you told me in that email. You didn't give me their information.
I thought I had it. Okay. That would explain. Anyways, just because I was thinking about digitizing. So yeah, there's lots of tricks. There's the cut tool, or there's actually 3 clips now that I think about it. There's the digitizing clip, where if you digitize, say you digitize the water boundary and then you realize you have islands. You digitize the islands on top of the water, you select the island, and then if you go to the digitizing pull down on the digitizing toolbar, you can use the clip tool and it'll take the water out from underneath the island, just leaving the island on top. Okay, you don't want things on top of each other. Yeah, that should do it. Okay, don't put it off too long. I would start digitizing maybe and see how well you remember. Give yourself an idea of how much it's gonna take you to do. I cut the area down a fair amount from what we did in the past. I hate digitizing, but I've had to do it, and I got paid a lot of money to do it, so it's worth going over again. I couldn't believe they were paying me to digitize, but didn't have anybody else. Probably need to put those lights. Were we here in class last Wednesday? Yep. Okay. My days are getting mixed up. Yeah, I was talking about cleaning this up. So yeah, you'd have all these sort of sliver, tiny little poly. What a mess this would be. And the way I'd clean it up would be sort of a mixture of dissolves and deleting really, really tiny polygons. It is an advantage of using the feature classes using a geodatabase because that updates the size automatically. Whereas if you were using shape files, you'd have to add a field and then you'd have to calculate geometry. Okay, so zooming in around there. Topology and cluster tolerance. Well, I think I'm going to get to cluster tolerance. So some methods for cleaning or preventing the slivers. Increase your cluster tolerance.
Are you sharing your PowerPoints?
And the cluster tolerance basically tells it everywhere there's an intersection, search this distance, whatever your cluster tolerance is, and if there are extraneous points or lines in that distance, snap them all together to minimize the number of slivers. You can trash your data this way if you set your cluster tolerance too high. And the cluster tolerance needs to be, whatever you set it to, it needs to be in the same units as the coordinate system. So if you're in geographic, you got to figure out what your cluster tolerance is in degrees. Usually it's a very small number, which is another, yeah, I usually use UTM. If it was in UTM, what are my units? Meters. If it's state plane, 4. State plane is 2. It can have 2 feet or meters. Dissolves, running a dissolve, saying remove the boundaries on all polygons that have this value in the attribute table that touch. And then going in and editing. Doing a sort on area. Then delete everything that has like 0.01 square meters because you know they're not really going to be useful.
Russ, your camera's off.
All right, don't worry about writing this down. You learn this at some point in high school or in junior high on how to figure out whether 2 line segments intersect. This is the same thing, but this is just an example of what the software is doing for every single line segment in the data sets. So each line segment has a starting point and an end point. I don't mean arc, I mean where the vertices, so between 2 vertices. So the more complicated your data is, the more often it has to do this. So you have 2 vertices on a line segment, a beginning and an end. those are the coordinates, and for line segment 1, line segment 2 is the other layer, and point A, so vertices A, vertices B. So calculate the slope for each line segment, and then calculate the y-intercept. Oh, maybe this was algebra. So the software does something simple like this, just figuring out what the slope is for each one. And calculate the y-intercept. And then I have 2 line equations for the line segments. Set them equal to each other. Okay, to figure out whether the lines intersect. How are lines different than line segments? Remember.
Lines are infinite, line segments are not.
Right. So if you set the 2 equations, if you do the simultaneous equations, the line equations, set them equal to each other, and you get a solution, it means if those lines are infinite, it will intersect. If they're not infinite, if they're line segments, then you actually got to see if the intersection falls on the line segment or not. Okay, again, we just press the button and let it run and hope it doesn't goof up. So that is what's going on in the background right now. That's why it takes so long on complicated data, not that it takes that long anymore. That parcel layer that I gave you at the beginning of lab 2, when you intersected it with the town, I probably would have had to run that overnight when I first started doing this because of all the intersections. Okay, so we're going to talk about topology because topology is key in the network analysis lab, which is now next week. It's topology, it's not topography. And what's happening a week from today in this class? Test. It's your first exam. I've not written it. So there will probably be a topology question. Don't tell me it's the shape of the land. So if we're talking about vector, topology starts out as points. The points can be vertices or nodes. And the point is the primitive unit. You can't break down a vector layer any further than points. So topology controls basically how things connect together, which is critical in vector because we start out with points, and if we want lines, we have to connect those lines. And if we want polygons, those lines have to connect back on themselves. There's something called a pseudonode, which we'll come back to. Nodes begin or end arcs and lines. You start digitizing a line. The first time you click to start a line, you've created a node. And then you start tracing something. Now you're entering vertices. When you double click to end that line, you're entering the second node. So a line can only have 2 nodes, except for, we'll come back to the exception. And then the vertices in between give it shape. If I don't have any vertices, what do I have? I just have a node, a start node, and an end node. I got a straight line. Okay, so those are my nodes, a start node and an end node. And the software keeps track of what was the first node created. That's going to be called the from node. It'd be nice if it called it start, but it doesn't. And then the last node, the one you double click to end it, that's the to node. It'd be nice if it called it end, but it's from and to. And so a couple of vertices to give direction. We're going to come back to that. Well, I will say, so every arc has at least two nodes, except there's one instance when it doesn't. We'll talk more about the pseudo node, but when might an arc only have a single node?
It's a point.
It's an arc. So it can't be just a point. Let me phrase it this way. When might an arc, on an arc, when might the from node be the same as the to node? A circle. The classic example is a cul-de-sac. Okay, you have an arc to represent the road, not a polygon, and then it closes on itself, so there's only a single node. But other than that, they always have two. They have a start node, or a from node, and a to node. That allows, keeping track of the from node and to node allows us to sort of build topology. We can control direction. When you Google directions in Google Maps and it tells you that you can't turn left here because it's one way, the wrong way, somewhere stored in there is they said traffic is only from the from node to the to node, not the to node to the from node, or vice versa. So we're going to come back to the pseudo node. I want to talk about it a little bit more. The vector is made up of arcs, points, and polygons. Where are the coordinates stored? In order for it to show up on the screen, we need coordinates, right? The line itself that connects the two nodes doesn't have any information. All that's stored is this node connects to that node. So all the points, all the nodes, and all the vertices are storing X, Y coordinates. And then somewhere, I mean, if that's all you have, you just have a point layer, that's all you need. But then if you sort of build that into a line layer, now you actually have to store not only the coordinates for each point, but which point connects to which. And then if you have a polygon, you have to store all that and the fact that it actually closes somehow, right? But still, in the software, in the background, the only thing that's storing the X, Y coordinates are the points. There's no real information on a polygon in the inside. It's the point, it's the nodes and the vertices that make up the boundary is what's being stored as coordinates. Okay, so some things about the vector spatial data model. We like vector. It works for us. It works for the way we sort of think about the world. It works on edges. Vector is set up so that if you cross a boundary, it's telling you the reason the boundary's there is because that thing is totally different than this thing. Parcels are sort of the easy example in that this polygon represents this piece of property, and if I cross the boundary of the polygon into the neighboring polygon, that's somebody else's property. So the point is used to represent the other types of spatial objects, lines and areas directly, requires external and explicit spatial index. The points do. So somewhere we're storing the X and Y. And if we have lines and areas, we're storing some information about how those points connect to each other. So requires external and explicit. It's worded that way because what's the other spatial data model we use? The raster's sort of spatial index is built in. It's not, it doesn't have to be external, and it doesn't have to be explicit. Okay, just because it's a grid and there's no gaps. So it's sort of built into the system itself. Whereas vector needs, you gotta sort, even if it's an imaginary coordinate system, you have to assign values to those points for them to fall where they belong. And then we have to keep track of what connects to what. Not true in raster. Spatial resolution is sort of limitless. If you're willing to spend the time digitizing, your spatial resolution and pretty much is infinite. Now, you zoom out, eventually it becomes a dot. We've all seen it. You zoom in too far and you're so far in you can't actually see anything. Was it Max, you had the 100-foot page that was it you that we couldn't zoom, we couldn't find your data?
No, that's me.
Somehow his data frame had been set to 100 feet across and proportionally long. So when we zoomed to a layer, it filled the 100 feet, but it was only an 8.5 by 11 page. That was a new one. I hadn't seen that before. Okay, so polygons. Lots of tiny little polygons. I think they're wetlands in the Adirondacks that I clipped from something, but I don't remember now. I can zoom in, or zoom out, I should say. They pretty much look the same. If I actually turn off the outline, it probably would have looked better when I zoom out. What happens is that the outline gets drawn last, so the outline sort of trumps everything. And then if I zoom in, they pretty much look the same still too. Right? If I spend enough time digitizing, I can keep zooming in and I still have wonderful detail. No curves. You can't do a curve in ARC. All you can do is tiny little line segments.
Can you do curves in other GIS?
I don't think so. I think everything is sort of set up. That's a really good question. I haven't tested it. I've only really used the software packages I've used. No. But if you're using something like CAD, which isn't really a GIS because there's no database, that does curves because you basically set a radius and it draws a curve for you.
Yeah. And I guess you could do a curve with buffers, or is that just a whole bunch?
If you zoom in on a buffer, you'll see that it's made up of tiny little line segments. Yeah. Okay, so advantages of vector correspond with the human approach to space. Sorry about that. We like lines. I mean, even if you think about it, elevation should not be vector. But we draw it with contour lines because that works for us. There's lots of things we can do with spatial relationships. We'll do this in lab, and that you're going to connect things from one side of Walt Disney World to the other. That just are not possible in rasters. Most maps are vector maps. It's very rare to see a raster-only map. Spatial resolution is limited only by practical considerations. Yeah, how much time you want to spend digitizing, how much storage you want to spend on it. Because every single point you add has an X and Y coordinate, which takes up space. Which leads to the next thing, storage requirements are lower when spatial complexity is limited. I don't have as many points to store. And even if you go back to before computer GIS, when there were actually still cartographers around, their maps were vector, they were just hand-drawn. You know, if you ever download any the historic topo maps, you know, those were all done with by hand at one point. Road maps, when people still had road maps. Though we were all vector. Forest maps, right? We use polygons for compartments. Even though we know usually the edge is not a defined edge. Home range. All the home range tools I've ever seen give you vector layers. I really doubt that that reflects reality somehow. I don't know. I don't deal with that life. The home range of a tree is much easier. Complex concept implementation. Rasters are simple in comparison. Okay, we're going to store all our XY data in the points. If we want to make it more complicated, we have to keep track of what connects to what and whether it closes. And then our attribute data has to somehow be connected to the features that are showing up on the map. Requires the explicit spatial index, so every point's got to have an X and Y. Some things are more difficult. Some things are easier. Some things are more difficult than raster. So buffers are simple. You can't do cost path, which is what I'm having to do the digitizing for. Because you're limited to only the features. If you have white space, You have area between, white area between your polygons. The software can't do anything with that. It can't make the connection. Surface modeling requires additional capability and analysis. There is a reason why most modeling is done in rasters. It's easier. Vector doesn't handle large contiguous areas very well. So there's a thing, so how vector handles it, there's a thing called a tin, which is made up of tiny triangles. It's actually how most computer games show landscape. You can't do any analysis, it's just sort of the finished product, even if it's elevation. You can't do anything with it because it's too complicated, and trying to write something that would access every single tiny little polygon is not really usable. So we switched to rasters because it's really simple to do stuff like that in rasters. I can 3 lines of code and I can step through every single cell in a raster, no matter how many cells. So if we're doing surface modeling, whether it's like dissolved oxygen, elevation, that sort of thing, we don't usually use vector for it. High spatial complexity requires large storage resources, and reality usually has gradual boundaries. That's a big one. Contours. We're saying anywhere on that contour has that same elevation. Well, what goes on in between the contours? All we know is the elevation can't go above or below one of the 2 surrounding contours. We don't know what's happening in between. Soil polygons. Who's in soils? 1, 2. Do soils really have a defined boundary if we haven't messed with them? They change gradually in between, okay? But if you download soil data, it's a hard boundary, and it's a totally different soil on the other side. Okay, so the primitive unit, this is just an example. So this is actually an old coverage. So back when I started and when we were using ArcInfo, if you had a polygon layer, built into the polygon layer was the line layer that made it up and the point layer that made up the line layer. And that's what this is showing. You can't, I don't think you can do that anymore. Okay, so that was the line layer that made it up. So each point has an X and Y. And then if it's a line layer, somewhere it's stored that which points connect to which. That's critical because if you don't have that, I mean, it could just zigzag back and forth or whatever, right? So we have to store that. And then to be a polygon, it actually has to close on itself. So when I was doing this, when we were still using these, if you digitize something, you digitized lines. And then if you wanted the polygons from it, you had to do what was called a build. And you ran a tool that took your lines and basically ensured that the lines actually intersected and closed. And if they didn't, it would leave the polygons out, which kind of sucked because you'd have to then go back in and fix it if you didn't do it. But that was how we sort of got all the individual layers. But like now we just do heads-up digitizing in polygons, much easier. That was the attribute table. F node to node. What does that sound like?
From node to node.
From node to node. So it's actually tracking which nodes connect to which. L poly, R poly. Nothing. Left and right. which polygon's on the left, which polygon's on the right. That's how Google can tell you which side of the street your destination is on. Okay, so that's sort of the topology that it was saving, and then length, and then the rest of its attributes. If we got in editing mode, you could not change anything from the left to through our poly. The rest of it you could edit, but those it wouldn't let you. Okay, so topology. You don't have to write this down. What am I doing on time? Oh. So topology and is a major study in major mathematics concerned with properties are preserved during continuous deformations of objects, such as deformations that involve stretching but no tearing or gluing. It emerged through development of concepts from geometry and set theory such as space dimensions and transformations. Okay, way beyond me. I just know about it. I read about it. That's about it. The idea in GIS is it's not quite this. But some of it applies in the fact that if you have topology built into your layer, you can go from geographic to state plane to UTM, which does stretch it. It changes its shape, and it should still be complete when you're done. Topology is a collection of rules that, coupled with a set of editing tools and techniques, enables the geodatabase to more accurately model geometric relationships. ArcGIS implements topology through a set of rules that define how features may share a geographic space and a set of editing tools. That works with features that share geometry in an integrated fashion, which does not sound a lot like that. Okay, it's actually a little disappointing when you realize what they mean. You can build topology into your layers. You can tell it that you can't have any lines that overlap or polygons that overlap. Might actually be worthwhile looking at that in the digitizing. And what it'll do is it'll take your polygons that do overlap and it'll find some place in the middle and have them share a boundary instead of overlapping. Parcel. There's something in ArcGIS called Parcel Fabric. They had a big push about 6 or 7 years ago to get surveyors to adopt it. And the Parcel Fabric was such that we know, theoretically, that parcels don't overlap each other. Right? No two people own the same property. In reality, that's not totally true. Okay. Because of mistakes in surveying, there are times where the property actually overlaps or there's a gap between them or something. The Parcel Fabric would not allow those gaps. It actually moved boundary lines, so they didn't happen. So if you're dealing with parcel layers, don't assume that they're accurate representation of where the boundaries are. Because it applies the topology rules so that there are no gaps, there are no overlaps. It moves things. For GIS, the coverage format has a strong topology, okay? You don't have to worry about it, but if you wanted a polygon layer, you had to build the polygon layer, it made sure everything connected, and if it didn't connect, you got errors and you had to go back in and fix them. If you wanted a line layer, same thing. Shapefile format has a really weak topology. Basically, all it does is say this connects to this, and this is the order. That's about as strong as it gets. The geodatabase format is going to depend on the user. Because you can actually, and we'll do this next week, you can create your feature class, you can create topology and say you don't allow any overlaps. Lines that are within a meter should merge to each other. There's like a list of things that you can set up as far as rules. They can be useful, they can trash your data. What they don't do is they don't make a copy of the data with the topology rules applied. They take your original data and they change it.
If you made a copy first and then edited that, would that solve that?
That's usually what you have to do. If you don't have a copy and you goof on the topology, you've ruined your data. Not a big deal for us next week because there's always going to be that copy up in the cloud for us, but okay, and then there's Tiger, Topologically Integrated Geographic Encoding Reference. So this was created for the US Census. It was sort of it was not the very first, but it's considered to be the first data set with topology. And they just wanted to track where people lived. We've collected all this data. We just want to know how many people live on this block. And we want to be able to do some simple analysis. So they had to store some encoding. And this went back to the 60s, I think is when this started. Where basically computers that filled this room would not have had the power of your cell phone that you take pictures with, text each other. We went to the moon with less processing power than is on your phones. Okay, so entire spatial relation between point lines and polygons is coded. Which block is on which side of the street, which house is on which side of the street, where the points might represent the houses, that sort of thing. The street would be a line, the block or the neighborhood or even the census tract would be the polygons. Okay, and so the census was really the thing that sort of started this encoding, this topological encoding going. And based upon the USGS DLG format, that's from the book. You won't see DLGs anymore, probably, which is good because they were kind of a pain to deal with. Topology always requires additional files. You may not see them. If you're dealing in geodatabases, they just get stored in the geodatabase. You can ignore it. We're going to use shapefiles for some network analysis next week. In order to use the shapefile, because the topology is so crappy, it creates other files that it then brings into the map with you. So it requires additional files for topology to be effective. Some advantages: ensures data integrity. If I have two roads that cross each other, do they actually intersect? If they intersect, there is a node where they intersect. If they don't intersect, there's no node and there's no way to go from one road to the other. So the difference between an overpass versus an intersection with a traffic light. Whether municipal boundaries line up, where the parcel layers actually line up. We got approached by the town of Saranac Lake many years ago, and they had a bunch of GIS data because Saranac Lake falls in 2 different counties. And their parcels didn't line up along the county line. So 2 students worked on that for their 420 project. We can do more if we have a stronger topology. Did anybody try and project the hydrology layer from Love Canal? The stream layer was called NHYD or something like that. I think I told you couldn't do it, but I didn't know if anybody tried. It won't let you project it because it doesn't want the topology changed. Built into the hydrologic data sets that you can download is basically the direction the water flows. Locational, one of the parts of the lab next week is built upon a 420 project where a student was heavily involved in his ambulance corps at home. They were looking for a new headquarters, and his project and his partner helped him using all the call data from the location of the call data from the previous years, and which would be, of the 3 potential places, which was the most centralized based upon the roads. Okay, so which location to pick? Apparently I have a blank slide. Okay, so going back to topology, right? Yeah. Not a big fan of that really first one I stole from Wikipedia. Not a big fan of the one from ArcGIS, but I'm a little biased against ARC. So your book, The Study of Those Properties of Geometric Objects That Remain Invariant Under Certain Transformations Such as Bending or Stretching. And then your book cited Massey 1967, which I've not read. But I think your book, that's sort of a nice description of it. That we can, if you build topology, you can project it to other coordinate systems. You can maybe move some vertices if you have to, but things still work if you have topology built. You can break the topology. It's totally possible. You remove a node where 2 lines intersect, and now you got no intersection. And now, if you use that for like network analysis, you can't go from that one where you can't make a turn there at that intersection because you remove the intersection as far as the software is concerned. Tiger data, first computer GIS, first have topology. The mathematical definition of topology only loosely fits how it is usually applied in GIS, which should be pretty evident now. That whole thing about, you know, the esoteric math and set value, you're going to look at the rules that you can choose, and there seems to be very little connection between what your choices are and what that Wikipedia quote said. You do more of this, it makes more sense, but it still seems a bit of a stretch. Okay, so some of this we've already talked about. So particular importance in vector data. Raster data has innate topology. You can't build topology in a raster data. You can't make it better. You can't make it worse. It just is. Vector, we have this wide range of things we can do. Requires the additional data files. Again, you're not going to really see them unless you're dealing in coverages, and you should not be dealing in coverages at this point. The advantages, so if I have topology, which side of the street I'm on, how to get from here to here. navigation. So the things you can do with network analysis, you can do like I was saying, where they found the best headquarters out of the 3 places. So this one's the best. The thing we all do in Google Earth or Google Maps is I'm here and I want to get to here. What's the easiest directions? You can do something called service area with a good topology, which is, this is my warehouse using this road network and basically speeds built into the road network. What customers are within half an hour of my warehouse. Okay, it can give you things like that, which you can't get with raster. Who tries to beat Google if you're driving? 1, 2, oh, I totally do. It's not fair, it updates as you go.
Yeah.
I think the best I've done is 5 minutes on it. Yeah, and now it added ways, so it tells you when there's a speed trap.
Yeah.
Every once in a while, though. I don't think it's not always active.
Yeah. I'm the person that says as he drives by the speed trap, no, there's no speed trap. I'm an older guy with white hair. I don't get pulled over. Okay, if you want to do cool stuff with vector data and topology, you have to use a geodatabase. You can't use shapefiles, and ARC doesn't like coverages anymore, which is too bad, but it's the way it is. So you have to use a geodatabase. You have to use either a personal geodatabase or a file geodatabase, but the personal geodatabase is going to go away when we go to ARC Pro. I don't know why they decided they couldn't use it, but once your data is in it, you have to build the topology externally. There's actually like, you right click on the geodatabase and say new topology, and you tell it which layers you want to build the topology for. And then you go in and look at the settings to choose. So you set the cluster tolerance. Basically, you're saying, much like with the vector analysis, if I have points or lines that are within the tolerance, it's going to merge them together. The best example I saw this, there was somebody was working on, they had downloaded the trails from the DEC from New York State. And there were a couple places, I don't know how they created them, but you could definitely see like a zigzag in the trail. There was no zigzag in the trail in reality. Somebody goofed in the digitizing, or there was an error, more likely in their GPS or something, like they lost lock or something. Because that zigzag of the trail, they were within a couple meters of each other, was it. So it goofed. Setting topology will fix that. Okay. All your layers, if you're going to do multiple layers, have to be in the same coordinate system. It can't and it shouldn't deal with the fact that, oh, I got some stuff in geographic, I got some state planning, I got UTM. It wants you to put them all in the same thing. Usually you don't use geographic for this stuff. List of rules: don't overlap, don't intersect, must overlap, must intersect, things like that. You'll see that next week. And then you get to rank the layers that are involved in the topology and say, this layer should not move, but you can move this layer all you want to make things work. Okay, and we'll stop there.